Good day, everyone. Today, I'll be speaking about crystalline waterproofing admixtures, what they are, how we classify them, and how we evaluate their performance. This talk is geared toward our expert audience of applicators, contractors, architects, and developers. We'll dive into relevant standards, EN and ACI, and highlight key test methods that ensure these admixtures truly deliver concrete durability under both absorption and hydrostatic pressure conditions. Introduction to crystalline waterproofing admixtures. Crystalline waterproofing admixtures are integral admixtures added to concrete to make it water impermeable. Unlike surface coatings, these admixtures work within the concrete matrix. The active chemicals react with water and cement byproducts to form insoluble crystals that fill pores and capillaries. This crystallization permanently seals the concrete's microstructure, preventing water penetration from any direction. In essence, the concrete becomes its own waterproof barrier. This technology is vital for structures like basements, tunnels, tanks, and foundations where we need the concrete itself to resist water ingress. Let's first clarify how crystalline admixtures are classified in standards. Under the European Standard EN 934-2, admixtures that make concrete watertight are classified as water-resisting admixtures. In EN 934-2, Table 9 defines the criteria for such admixtures. Traditionally, these have been hydrophobic or pore-blocking products that reduce capillary absorption, often by causing water to bead off the concrete surface. To meet EN 934-2's requirements, an admixture must significantly reduce the concrete's water absorption. For example, EN 934-2 requires that concrete with a water-resisting admixture has less than or equal to 50% of the capillary absorption of a controlled concrete after 7 days of curing and 7 days of testing. This essentially gauges how well the admixture limits water uptake under low pressure, capillary action conditions. However, crystalline admixtures don't fit neatly into the old EN 934-2 mold. According to the new European assessment document ACI 212.3R, crystalline products are not considered ordinary water-resisting admixtures because they behave differently. EN 934-2's capillary absorption test isn't appropriate for these types of admixtures. Why? A crystalline admixture might not show a big effect in a simple absorption test, yet it can dramatically reduce permeability when the concrete is subjected to water under pressure. In other words, it excels in true waterproofing, high pressure scenarios rather than just damp proofing. This recognition led to the new EAD classification called waterproofing admixture for concrete, distinct from the EN 934-2 category. In the American context, the American Concrete Institute, ACI, provides a similar classification in ACI 212.3R 16. ACI distinguishes between PRA, permeability-reducing admixtures, for different conditions. PRAN, permeability-reducing admixture for non-hydrostatic conditions. These are basically damp-proofing admixtures used where concrete is not exposed to significant water pressure. They typically work by repelling water or partially blocking pores, using soaps, oils, or fine fillers. PRANs reduce absorption, but offer very limited resistance to water under pressure. PRH, permeability-reducing admixture for hydrostatic conditions. These are true waterproofing admixtures that can withstand water under pressure. They usually form crystalline growth or stable plugs in the concrete to block water ingress. PRAs are suitable for watertight construction, e.g. water tanks, deep foundations, and are sufficiently stable to resist high hydrostatic pressure. In practice, hydrophobic admixtures, like stearate-based products, fall under PRAN. Non-hydrostatic, they keep water out when it's just damp or rain exposure, but cannot stop pressurized water. Crystalline admixtures, on the other hand, are categorized as PRH, hydrostatic. They reduce water penetration through crystalline deposits and remain effective even when water pressure is applied. In fact, Industry literature notes that crystalline admixtures are admixtures the most effective PRAs, with clear advantages in sealing microcracks and providing long-term waterproofing durability that hydrophobic admixtures can't match. So, to sum up classification, EN 934-2, Table 9, gives us the water-resisting admixture category, think pran-type behavior, whereas the new EAD 260026 and ACI PRH category recognize crystalline admixtures as a distinct class of true waterproofing admixtures designed for hydrostatic conditions. Now that we know the categories, let's talk about performance evaluation. How do we prove that a given admixture actually works? This is where specific test methods come into play, and it's critical to choose the right tests to reflect real-world conditions. EN 934-2's test focus. The traditional test used for EN 934-2 Table 9 compliance is a capillary absorption test. In the EN standards, this is essentially measuring how much water a concrete sample absorbs through capillary action over time, with no externally applied pressure. There is a standard test method, EN 480-5, sometimes referenced in the context of EN 934-2, that determines the capillary water absorption of mortar or concrete with and without the admixture. In simpler terms, you cast two concrete samples, one normal and one with the admixture, and after curing, you expose them to water, often by partial immersion, and measure how much water is absorbed or how far it wicks in. To pass as a water-resisting admixture under EN 934-2, the treated concrete must absorb significantly less water than the untreated concrete, as mentioned, less than or equal to 50% at 7 days in one of the criteria. This absorption test is great for evaluating admixtures that function by making the concrete surface hydrophobic. If an admixture works by poor blocking or water repellency, the capillary absorption will drop dramatically, you might see water beating on the surface, and very little gets sucked into the concrete. So, standards like EN 934-2 effectively set a baseline. Does the admixture reduce absorption enough to classify as water-resisting? However, real underground waterproofing is about more than just surface absorption. It's about resisting water pressure pushing from the outside. A simple absorption test at atmospheric pressure doesn't simulate the scenario of a basement wall holding back groundwater. This is where the new EAD 260026 and its testing approach come in. The EAD draws a clear line. Water-resisting admixtures are tested with low-pressure absorption, but waterproofing admixtures must be tested under high hydrostatic pressure. In fact, the EAD explicitly states that an absorption test alone is not suitable for evaluating permeability reduction for crystalline admixtures because those require water pressure to activate fully. Instead, the key performance test is the depth of water penetration under pressure, as per EN 12,390-8. EN 12,390-8 is a standardized test for water impermeability. You expose one face of a concrete specimen, usually a cube or cylinder segment, to high water pressure, typically 0.5 MPa, about 5 bar for a specified duration, usually 72 hours. After this, you split the specimen and measure how far the water penetrated into the concrete, the wetted depth. The shallower the penetration, the more waterproof the concrete. This test directly gauges the concrete's ability to withstand hydrostatic pressure. Under EAD 260026, a waterproofing admixture is evaluated by casting two sets of concrete, one without the admixture, both with a standard mix design, e.g. semi-cement, with C is almost equal to 0.60, and then performing EN 12,390-8 at 28 days age. The difference in penetration depth indicates how much the admixture improved the water impermeability. The contrast between these two tests, capillary absorption versus pressurized penetration, is crucial. Many hydrophobic admixtures that easily pass the absorption test might fail to stop water under pressure because they only create a surface barrier. As one technical expert put it, absorption tests do not accurately reflect the performance of concrete admixtures designed for resistance to hydrostatic pressure. A vivid analogy: a water-repellent admixture in concrete is like a Gore-Tex jacket. In light rain, the water beads up on the surface and nothing gets through. But if you dive into a lake with that jacket, water will eventually force its way in. Similarly, a concrete treated only with a Pran-type admixture can still leak when subjected to significant groundwater pressure. A crystalline PRH admixture, on the other hand, actually plugs the pores internally, like sealing the fabric itself, so it can withstand that lake-like hydrostatic pressure. To emphasize this difference, EN 934-2 versus EAD 260026 is essentially absorption test versus pressure test. By integrating EN 12390-8 as a requirement, the EAD ensures that the admixture's performance is proven in conditions akin to an underground structure with water pressure. This is a far more real-world evaluation of true. Waterproofing aside, concrete must still meet structural requirements. Adding an admixture, especially a powder that may include fine fillers, could potentially affect the concrete's strength or other mechanical properties. Thus, part of performance evaluation is confirming that the structural performance of concrete is not compromised by the admixture. European Standard EN 12390-5 covers testing the flexural strength of concrete beams, while compressive strength is more commonly checked, and EN 934-2 actually mandates that 28-day compressive strength of admixed concrete be at least 85% of the control. Flexural strength testing provides insight into the concrete's tensile behavior and overall integrity. Specifying a flexural strength test can be an auxiliary method to validate that the waterproof concrete still behaves as expected under load. In practice, most crystalline admixtures have a neutral or even slightly positive effect on strength. The internal crystal growth can densify the matrix, sometimes yielding equal or higher compressive strength compared to plain concrete. Many manufacturers report meeting the greater than or equal to 85% strength criterion easily, and often end GT 100%, i.e., some strength gain due to poor refinement. By testing flexural strength per EN 12390-5, engineers can ensure, for example, that a wall or slab with the admixture will not be more brittle or prone to cracking than normal. It's essentially a quality assurance step, the concrete's load-bearing capacity in bending, and by correlation, its toughness, remains sufficient for structural requirements.